Hello, my name is Ali. I'm a third year PhD student at the University of Illinois Urbana-Champaign, and today I'm going to present AlphaTrans, a Neuro-Symbolic compositional approach for repository level code translation and validation. This work is a collaboration between University of Illinois, IBM Research, Indian Institute of Science, and Cornell University, accepted at International Conference on Foundations of Software Engineering 2025. In the beginning, let's start with understanding what's the problem of code translation. Code translation is the process of converting source code from one programming language to another. Let's suppose we have this Java code here on the left, which prints the numbers between 0 and 4. Its translation in Python is shown in the code snippet on the right. Code translation is a challenging task because it requires understanding of syntax and semantics of the code both in source language and in the target language. So there are some research gaps in this domain, specifically in the translation component. It demands for idiomatic code in the translations, and so there's also a need for like translating repository level code. Existing transpilation techniques can scale to repository level code, but the problem with them is they produce unreadable and in most cases non-idiomatic code. LM-based techniques can produce more readable and idiomatic code, but the problem with them is they do not scale to repository level code because of their like limited context window size. The second component is the validation. So the problem is existing work is treating the translation and validation components as the separate processes, and it can cause the problem of um, if there's something wrong in the validation, there might be a need to redo most of the translations. So there's also like making the problem of like debugging harder because once we have these two processes like separated, it's hard to generate a patch in case the validation says that a fragment is not functionally equivalent. In order to address these two research gaps, we propose a Neuro-Symbolic approach for the translation component, where we like combine the power of the program analysis and generative AI in order to address the problems of idiomaticity and scaling to repository level code. And for the second one, we propose unifying the translation and the validation phase into a single component, such that we translate fragment by fragment and we perform validation checks right after the translation of that fragment is completed and check for compilation errors and make sure that the translations are functionally equivalent. Therefore, the name Neuro-Symbolic Compositional Translation and Validation. So to that end, we propose AlphaTrans, which is a Neuro-Symbolic approach for end-to-end repository level code translation and validation. It has three main components. Let's go deeper to every component. The first one is program transformation and decomposition. So in here, this component, specifically the transformation one, refactors like source language specific features like method and constructor overloading circular dependencies um, into more like universal representations so that they can be easily translated to target languages. For example, method overloading is a feature in Java, but in Python it's not straightforward to implement that. Second, AlphaTrans breaks the like repository level code into smaller fragments in order to address the limited context window of small open source models. Finally, it also decomposes the tests as well in order to make sure that um, the bugs can be localized easily by executing tests in a certain order. The second component is skeleton construction and type translation. AlphaTrans ahead of time before translating the method bodies, it first builds the project skeletons in target language and uses it for compositional translation when we go fragment by fragment. In order to achieve this, it requires an initial type resolution in order to make sure that the types are compatible between the source language and the target language. The next component is the compositional translation and validation phase, where we reverse the fragments in a topological call order and make sure that the um, fragments with no dependencies are translated first, and then fragments with dependencies are translated later. This makes sure that we always translate a fragment whenever all its dependencies are previously translated. Next, we create the prompt using the skeletons that we built ahead of time, and ask an LLM to provide a translation based on the context that we provide for it. Once we take the translation, we check that it's syntactically correct, compilable, and it passes all of our translated tests on that specific fragment. In order to address the test translation coupling effect, which is the problem of a test is not passing, not because the fragment we are focusing is incorrect, but because some other fragment in the call chain is incorrect. So in order to address that, we use GraalVM for our in-isolation validation technique. Using GraalVM helps us to validate the correctness of a specific fragment only for that fragment. It's not going to be affected by the incorrectness of other translations. We keep the translation we keep the fragment that we translated in the target language and keep the rest of the code base in the source language, and then we execute the eligible tests. In order to evaluate AlphaTrans, we choose 10 large-scale Java projects and we translate it to Python. For the large language model, we use DeepSeek Coder 33 billion in order to make sure our results are reproducible. This table here shows the 10 subject projects that we use in our study. In total, we have 836 classes and over 8,000 methods. So remember, we have the type resolution component. This ATR column shows the automated type resolution result. So AlphaTrans can automatically resolve 91.99% of types from Java to Python. And also the SV column shows the skeleton validation results. So when we build the skeletons ahead of time before the method body translation, we run some checks in order to make sure that there are no runtime errors in Python. So overall, we achieve a 100% skeleton validation success in all our projects. Now, in order to measure the effectiveness of AlphaTrans in translating and validating real-world Java projects, so let's focus on this table. It shows our 10 projects and their AMFs, the second column. AMFs is showing application method fragments. So application method fragments are the fragments which the actual logic of the projects are coded in those fragments. And these are not the test fragments, which is coming from test classes or test suites. So these are basically only the application methods coming from application classes. In Java, these are mostly under source main directory. So overall, AlphaTrans achieves 98.8% syntactical correctness. Syntactical correctness meaning that with the prompt that we build using the skeletons and ask an LLM to translate it, the translation taken from the LLM is syntactically correct 98.8% of the time. It also achieves 25.14% functionally equivalent score, which is the sum of Graal success and M1 all. So Graal success shows the percentage of fragments which GraalVM, being our in-isolation validation, achieved success. So GraalVM achieving success meaning that we collected all of the eligible tests and we executed all of them, and if all of them pass, we consider that fragment to be Graal success. And in here, the column M1 shows the number of fragments where GraalVM could not validate it because of the sum of limitations that GraalVM has. But test translation, which is our alternative validation technique, it could successfully validate it. So column M1 all means that all of the eligible tests that were translated, all of them passed, and M1 sum means it's like some of those tests pass. So functional equivalence here means that like the sum of all GRAL success plus M1 all. Also, AlphaTrans achieves around 27% runtime behavior validation, and this is the sum of GRAL success and M1 sum as shown here in the table. We also check the idiomaticity of the generated Python code from those 10 projects using PyLint, and AlphaTrans achieves a score of 10 out of 10 based on the idiomaticity of the of the generated translation. So we took every fragment, executed PyLint on it with specific flags, and we were able to get a score of 10 out of 10. Next, we also investigated how long does it take to fix. So AlphaTrans is definitely not the perfect system, and it can generate some incorrect translations. So from our 10 subject projects, we took 4 of them, and we used 2 software engineers in order to manually investigate the translation bugs, manually repair them in order to complement AlphaTrans, in order to achieve all green tests. All green tests meaning all of the tests that were translated, change all of them to pass all the failing tests. So among the 4 projects are file upload, CLI, CSV, and validator. And as you can see, for example, for file upload, it takes around 5 hours in order to make 120 line additions and 114 line deletions in order to achieve all passing tests. So without AlphaTrans, translating and validating each project can take several days, if not weeks. But with AlphaTrans, it just it's actually taking very short time, helping the developers in order to translate and validate their code bases much faster. We also studied the impact of test suite quality by generating more tests using the Evo suite. So we augmented the original test suite with Evo suite and decided to see what's the impact of the better, more focused tests. So in here, as you can see, we have the column showing the average number of methods executed for each test. So we noticed that in developer written tests, each test is on average executing like 22 methods. That's why causing a very long call chain. And the problem here is that from those like 22 methods executed, if one method in between is incorrect, the execution can stop here, or it can affect the behavior of the methods which are later executed in that chain, like creating a problem and casting a shadow on the execution of the other methods. But with EvoSuite, when we collected these stats, we noticed that on average 11 methods are executed. So meaning that we have more focused tests with EvoSuite. And this, evaluating AlphaTrans with this new test suite has increased our true positive rates by 6%, around 6%, and our ATP score, all tests passed, by 2%. So these are percentages added extra on top of whatever we had in the previous slide. So in conclusion, we can see that high coverage test suites with focused unit tests are the key for test-based translation validation, not the Graal VM1, but the test-based translation validation, where you translate the test and use that in order to validate the correctness of the translation. So AlphaTrans is just the beginning of repository level code translation and validation. There are a lot of challenges that still are an open problem and needs to be addressed. The first one is translating library APIs. This is a big problem right now, specifically for open source LLMs, where they hallucinate and cannot translate the APIs from one language to another. For example, in here, you can see we have a calendar class, which is trying to set the First, create a calendar object and set the month to January by using index 0. So in Java, index months are indexed between 0 and 11, corresponding to January until December. But then the original translation by the model also uses 0 in Python, as you can see in line 3 on the right. But the problem here is months in Python are indexed between 1 to 12. So the correct way to set the month to January here is to basically set it to the month equals 1. So as part of our manual investigation and human study, we fix such kind of problems. But the LMs are yet to understand these deeper problems and like translate this fragment properly. Another problem is implementing non-existing logic in target language. For example, in Java we have the problem. In Java we have like iterators where their behavior is not like the iterators in Python. Um, in Java, the iterator has dot next and dot has next calls, where dot has next is just returning a boolean without advancing the iterator to the next element. But in Python, that dot has next does not exist. And whenever we call next every time, it advances the iterator to the next element in Python. And in order to avoid this problem happening, we need to implement a whole class called peekable iterator and wrap our existing iterator inside it in order to like manually implement the implementation of dot has next as shown on line 6 here on the right. Another problem is like in order to like teach the LMs to deal with corner cases, like for example typecasting. In the code snippet on the left, the Java source code, whenever we have a null string, which is of type null, and try to concatenate it with a string, uh, it actually performs implicit typecasting and does not throw any kind of errors. But in Python, if we are trying to concatenate a none with a string, we will have a exception thrown, and that's a big problem. So in order to take care of this, we need to first cast explicitly the null string to a str and then concatenate it. Like automated type resolution is another problem, and it's an open problem that we need to move it on. Remove the need for manual investigation of translated types in order to have a high quality type map between any pairs of languages. And we also need to have like better in isolation like validation techniques. We noticed that GraalVM has its own limitations, for example, state sharing. And another problem with GraalVM is it's only limited to a handful of PLs, like 6 at most. And that's a big problem because we have a lot of other more like programming languages that we could like translate and validate. Uh, we can have in the future other forms of translation validation, for example, runtime verification and also formal verification of specific properties like concurrency. And yeah, so translating arbitrary pairs of like programming languages is another problems. It's a holy grail that we need to achieve in the future. We're a bit far from being like PL agnostic right now. Every tool that is trying to address this problem is built for a specific language pair. For example, in our case, Java to Python. But yeah, so building tools which are PL agnostic is going to be very challenging, and it's actually an open problem. Yeah, so this was basically the presentation of our paper, AlphaTrans. Feel free to scan the QR code or use the link below to visit our GitHub repository and try AlphaTrans on new projects. Um, if there are any issues, please feel free to open an issue on our issue tracker. Thank you so much.